Okay, hello. Welcome to topic 2 of PYC3704 UNISA Psychology. If you haven't already done so, please like, share, and subscribe. I don't recommend the notification button, but that will help me. I'm halfway through to getting a monetized YouTube channel. So, before we start topic 2, just note that in the previous chapter, question 24, the correct answer is 2, not 3. Okay. So if you clicked 2, you're not going crazy. You are right. Oopsie. All right, let's continue. So, there are some important phrases in the overview. Okay, for example, formal research is a process of testing hypotheses. That is a particularly useful phrase to remember. And how we figure out if these hypotheses are true or false is through probabilities. So we figure out if these are probably correct. Okay, probabilities are a distribution of possible outcomes. And we do pay a lot of attention to the concept of normal distribution, which is normally represented with a bell curve. Okay, let me just show you the bell curve. See what's going on here. Oh, one moment. Oh, I see what it's done. There we go. Okay, so normal distribution is what we depict with this diagram here. Okay, that is a bell curve. All right, so correlating conceptually with normal distribution, a few other concepts. So let's see what they are. Standard normal distribution. Okay. Sampling distribution. Central limit theorem. Okay. All right, so let's go ahead and get started. We aren't going to do a lot of math, but I do recommend going and doing the math separately so that you feel in control. And I recommend Allison. There's courses aimed at high school students that are perfect for us and, in fact, quite daunting in the beginning until you've practiced quite a lot. Okay. Okay, so here is an important sentence. This is the kind of sentence we are going to be learning to use. The difference between the two groups is statistically significant because the probability of obtaining these results by chance is very small. In other words, it's likely that the difference between the two groups is not the result of math that isn't precise enough. It's the result of real differences out there in the world between the two groups. Okay. And then looking at, okay, well, how are they different and why might that be so? And how can we interpret that? And this is very, very, very important information for making decisions and for science. Okay, so there's 3 types of probability. There's intuitive or subjective probability, where you assess probability based on your gut feeling and on your own informal generalizations, not very well thought out, but felt out as from day to day and moment to moment. We use that all the time. Then there's, if you want to know the probability of something happening, you run the experiment thousands and thousands and thousands of times. And when you add up the number, you say that's the probability. It's empirical or frequentist. Okay, and there's going to be a very interesting experiment later on in this chapter around that. Then finally, there's classical probability, which is mathematical and reasoning deduction. Okay, So we're going to be looking at the classical and also at the empirical, but mainly at the classical. Okay, so in classical probability theory, the outcome you're trying to evaluate the likelihood of is called an event. Okay. And it's actually called the favorable event. Then all the other possibilities are called outcomes. So probability, if we're looking at the probability of something happening, the probability of an event is the number of favorable events divided by the number of possible outcomes. For example, if you're flipping a coin and you're looking for the number of heads, there's two possible outcomes, heads or tails, and the number of favorable events is 1 over 2, which is 50% or 0.5. That's the probability. Okay. And the probability of tails is also 0.5, and you'll see that that adds up to 1. All the possible outcomes add up to a probability of 1, and you'll see that again later. Okay, so with heads and tails, if you've got a fair coin, it's not bent or distorted in some way, the number of those two possible outcomes, those two events, are equiprobable. In other words, equally likely to occur. Okay, so now we're going to go into looking at balls in a bag or a box problem. So if we've got 4 balls, each a different color, and we throw them all into a box and pick one at random, the probability of selecting one ball, this is very easy and we can understand it intuitively, is 1 in 4, which can also be written as 0.25. Okay? Now, I want to show you a way that this can be drawn out, which is quite useful. Okay, you can draw it as 4 possible outcomes in a little grid, and that will come in handy in a moment. Okay, so say you want, so here we can easily see that it's 1 in 4, right? Probability of drawing a red ball out of the 4 is 1 in 4. You can see that at a glance. Say we are going to draw 2 balls, and we want to know the probability of drawing a red ball and a yellow ball. Okay. Now, if you don't put the first ball back in, if you put the first ball back into the box, so you draw your 4 balls, and then you draw one, you go, oh, it's red, and then you put it back in. What's the probability of drawing a red ball? Okay, there's 2 ways this can be. You could draw the yellow first, and then the red, or the red first, and then the yellow. And if you look at this, there's 2 blocks of 16. The probability of drawing a red and a yellow ball is 1 in 8. Now let's go to the puzzle in the book. So they're saying you draw 1 ball, you don't put it back in the box. Now you've got 3 balls in that box, okay? So it means you can't draw the red ball twice, or the yellow ball twice, or the green ball twice, or the blue ball twice. Now what's the probability? We just count the blocks. 1, 2, 3, 4, 5, 6. So there's 12 uncolored, there's 12 blocks that aren't grayed out. 2 of those are possible. So it's 2 over 12. And that 2 over 12 equals 1 over 6, which is 0.167. Okay? So that's one way of figuring it out. And I recommend drawing whenever possible because it's just intuitively so much easier. And then you go back to the math and get your brain familiar with the math and the way that it's denoted. So if you look here, this formula says probability of a red ball equals 1 over 4 possible favorable event over possible outcomes. 1 over 4 is 0.25. Now we're looking for yellow and red. Okay? And it doesn't matter which order they're in, but we're not putting the ball back in afterwards. So we're going from 4 balls to 3 balls to 2 balls there in that box and 2 balls in our hands. So it could be red, then yellow, or yellow, then red. So red and yellow, red and blue, red and green, yellow and blue, yellow and green, blue and green. Those are the possible combinations. 6 of them, right? So then we say one of those is the one we're looking for, this one here. So the probability of drawing a red and a yellow is 1/6, which is 0.167. Okay, and you could do the same thing with the heads. There's a diagram of it. Okay, cards, same thing. Say you're drawing the number of aces, 52 decks in a card, cards in a deck, 4 aces, 4/52, 1/13, 0.0769. Now with 52 cards, you don't want to do a grid. It can be a little cumbersome, right? But it's possible. If you're not sure and you want to go ahead with that, you can, especially with Excel, where you could color in most of them with just pulling the mouse down. Okay, and that can help you with difficult puzzles. The relative frequency approach. In general, the theoretical probability of an event can be approximated by the relative frequency or proportion of times that the event occurs. Hence, the probability of an event is the number of observations of the event over the number of times the experiment was performed. So this is for the empirical approach to probability. Say you want to find out how many times something happens. You just run that experiment thousands and thousands of times. For example, n number of heads is 1 million flips of the coin is 1/2 is 500/1,000,000, which is 0.5. Okay? So that is a random experiment. So here we use experiment as a term very broadly. It means any process of observation and measurement. Okay? And the outcome of a statistical experiment is a random variable. It's called random because its value cannot be predicted and is known only after the experiment has been performed. You cannot know it in advance. Basic terminology related to the theory of probabilities. Okay, so all of those possible outcomes are called sample space. So, for example, that's why this is so nice. You can see there's a sample space of 12 possible outcomes, okay, or 16, depending on how you run the experiment. Okay, whether you put the ball back in after you've taken out once, then you've got 16 possible outcomes. If you take it out and keep it in your hand while you're getting the other ball out, then there's only 12 possible outcomes. And that is the sample space of 12, sample space of 16 possible outcomes. So you can map it out in 2 dimensions here. Okay. Another way to write a sample space is with a set, like this. Okay, so it's S, the sample space, equals open curly brackets, heads and heads, semicolon, heads and tails, semicolon, tails and heads, semicolon, tails and tails, and close the curly bracket. Okay, so it's worth writing this out in a notebook just to familiarize your hand and your eye and your brain with this language. If you throw a 6-sided dice, there's your sample space, denoted with those brackets, holding each possible outcome and closing the set at the end. Okay. So when we interpret probability as a relative frequency, we follow the law of large numbers. The law of large numbers is that if an experiment is done repeatedly and if the outcomes are independent of one another, the observed proportion of favorable occurrences of an event will eventually approach its theoretical probability. In other words, if you flip a coin 1,000,000 times, you are almost certain to find that your probability calculated at the end is 0.5. Whereas if I flip a coin 3 times, it's not going to be 0.5. It can't be 0.5. I'm going to flip it. I'll get one head. That'll be 0.33 as an outcome. I'll flip it twice, I get 0.67, okay? So the smaller your number, the less it is determinable with the theoretical calculation. The bigger the number of experiments, the closer it'll approximate to the theoretical number. Okay. Okay, so probability is quite difficult to grasp because it's counterintuitive. We have a kind of an innate sense of math that if I have two things and one, I don't have one, then I have one. There's an innate arithmetic which our brains are quite comfortable with, okay, and which our brains work well with. But this is not true with probability theory. Probability theory is counterintuitive. In other words, what your intuition tells you is the correct answer is often the wrong answer. So, for example, the gambler's fallacy. If I'm playing cards and I don't see the gambler's fallacy, okay, you see, it does work, is an intuitive sense of probability, such as if I'm playing cards with people and I haven't seen the ace of spades come up and I need the ace of spades and it hasn't come up for a while, I can intuitively say, oh, well, it's probable that it's still in the deck. No one's played it. And intuitively and probably logically, that is probably quite a good guess. But if I'm throwing a coin and I don't get heads for ages, my brain tells me it's time for heads to come up. And this is not so. The dice, the coin has no memory. The probability of coming up heads or tails is exactly 0.5. It's the same. Okay, gambler's fallacy. But this is very interesting. This is like an ESP experiment where ESP was proved statistically by asking people to beat the odds on predicting which cards would be drawn next. And there were other experiments also asking people to influence which card would be drawn next, or what number would come up in a random number generator or something like that, that were also have had some very interesting results, but have also been, so anyway, that's very interesting, the Ryan cards. Okay, we hit 18 minutes. I think that is probably enough for one short lesson. Let's take a break and continue with it soon.